All right, so let's start talking about this one sample t-test. And with a one sample t-test, again, we're going to be trying to establish whether the true mean value for a population is likely to be equal to some value or not. And so what I'm going to draw here is a sampling distribution for a population, assuming that the null hypothesis is true. So fill in some of this here before I talk. All right, so we're going to call this a sampling distribution if the null hypothesis is true. So if you recall from before, our null hypothesis is that the true population mean is equal to 5. Our alternative hypothesis is that the true population mean is not equal to 5. So if our null hypothesis is true, we're going to say that the actual true population mean is equal to 5. This means that if we were to create a sampling distribution to tell us the likely means of the different samples we could get, we put in 5 here for our mean of the sampling distribution. And this particular sampling distribution is going to be a t-distribution. And as I said last week, the t-distribution was going to soon become our friend, so here it's back. But again, a t-distribution is almost the exact same thing as a normal distribution. The only difference is that when you have small sample sizes, it's a different shape. But right now, with our sample size of 100, this thing is actually just looks exactly the same as a normal distribution. And what we're going to be trying to do is figure out whether it's likely that we got a sample mean of 10.6 from a distribution that looks like this. In other words, this is the distribution if the true sentence length in the population is really 5 years. So these are our sentence lengths. And if it's really 5 years on average, how likely is it that we'd get a sample mean of 10.6? And is it something that we could expect to happen pretty often, or is it something that would happen relatively rarely? And we're going to use the sampling distribution to answer this question. And when we talk about t-distributions, we're going to talk about the same sort of parameters that we had for the normal distribution. In other words, for our sampling distribution, we have an overall mean, and we're going to have a standard error as well. And as I put in that very last bit of the last lecture, the standard error for our t-distribution is going to be written like our estimated standard error, which we call S sub x bar. And this is something that we're going to need to calculate, just as we calculated the standard error for the sampling distribution using the normal distribution. So let me just back up for a second. So we get our true mean value here the same way that we would get a mean for a sampling distribution using a normal distribution. And the mean for the sampling distribution is equal to the mean for the population. And again, we're talking about a population that is what we're saying is true in our null hypothesis. So if our null hypothesis is that the population mean is equal to 5, the overall mean of our sampling distribution is going to be equal to what we said in the null hypothesis, so 5 years. To finish finding the parameters for this t-distribution, we're going to use this estimated standard error formula that we met last week, where, as I've written sort of messily there, your estimated standard error is going to be equal to the standard deviation for your sample divided by the square root of n. And I'm actually going to just rewrite this in sort of a less wiggly way. So our estimated standard error is going to be equal to the standard deviation for the sample divided by the square root of your sample size. And again, the standard error is the standard deviation for your t-distribution, and it just tells you how wide or narrow it is around your mean. So this has the exact same meaning as this bad boy that you might remember from the normal distributions. The only difference is that this one's for a t-distribution. But I'll get rid of that for now. All right, so in order to start answering this question, we have to fill in these parameters. And so we're going to calculate our estimated standard error using this formula. So I'm going to fill in the rest of the information that we had on the example in the slides. So our sample standard deviation was equal to 5.8, and our sample size was equal to 100. So this here is x bar, this here is s, and this here is n. So our standard error is going to be given by this formula. We're going to plug in 5.8 for the numerator for the sample standard deviation, and we're going to plug in the square root of 100 here for the square root of n. If you do this math out, you get 5.8 over 10, and that gives you 0.58. So that tells us that in this sampling distribution, which is the sampling distribution that you'd get if the true population mean really was 5 years, we'd have a mean of 5 and a standard error of 0.58. And we're going to need this information in order to calculate our test statistic. So as I said before, the first step in doing a hypothesis test is to write out null and alternative hypotheses, which we have right here. The second step is going to be to calculate a test statistic. And similar to last week, I'm going to go through this example where I explain in great detail each of the steps I'm doing and why I'm doing them. And after that, I'll also go through an example where I do everything a little bit quicker and where you just focus on the nuts and bolts of what you actually need to be able to do. So the test statistic in our t-test is going to be some t-statistic. Which we'll refer to as t. And a t-statistic, again, has the exact same meaning as a z-score. So on a standardized t-distribution, how far away in terms of standard errors from the mean is our sample statistic of 10.6. The nice thing about t-statistic is that it's really very similar to the z-score in every way, including how you calculate it. So our formula to calculate t is going to look like this. And in order to calculate our t-statistic, we're going to plug numbers into this formula that looks a whole lot like a z-score formula, except that instead of having sigma sub x bar here, we're going to have s sub x bar here. And the difference is that, again, this is our estimated standard error that we're estimating based on the sample standard deviation, rather than an actual standard error that we'd get from the population standard deviation, which is what we used when we were calculating z-scores. So looking at our t-statistic here, I'm just going to write out what these different parts mean. So x bar is our mean. Mu sub x bar is our sampling distribution mean. And s sub x bar is our sampling distribution standard error. So we have all these things calculated already. And this means that we can just take what we have on the top half of the sheet and start plugging it in. So if we want to calculate our t-statistic, we're going to first look at our sample mean of interest. In this case, our sample mean is 10.6. We're going to subtract our sampling distribution mean. And again, we're basing this off the sampling distribution. That's what we would see if the null hypothesis were true, if the true mean sentence in the population really was 5 years. So we're going to plug in 5 for that, because that's the mean of our sampling distribution. And finally, we're going to plug in the estimated standard error here. And the estimated standard error is what we just calculated using our sample standard deviation and sample size. And again, it's the standard error for this t-distribution that we have right here. So that comes out to 0.58. And if you plug in all this stuff, you should get a test statistic of t equals 9.66. So 10.6 minus 5, and then all of that divided by 0.58 comes out to 9.66. So this here is our test statistic, which in this case is called t. And what this tells us is where on that t-distribution our sample falls. So what I'm going to redraw here is the t-distribution but standardized. So this here is going to have the same meaning as a standard normal distribution, where it has a mean of 0, a standard error of 1, and we can put our t-statistics on this distribution in the same way that we would put our z-scores on a standard normal distribution. So what this tells us is that our sample out here is at a t-statistic of 9.66. In other words, we are 9.66 standard errors away from the mean. So this is obviously not drawn to scale here since I just wrote a 1 up here. But what this tells us is that we're 9.66 standard errors away from the mean. If it were drawn to scale, it would probably look something like this, where we're actually really, really far out away from our mean. So again, the test statistic that we just calculated tells us where on this t-distribution our sample statistic falls. In other words, how far away are we from the mean of our t-distribution? And if you think about it, going back to this one where we have all the numbers filled in for our world where the null hypothesis is true, it's telling us that our sample statistic of 10.6 years is 9.66 standard errors away from our mean of 5. Okay, so what do we do with this information? Well, the final step is going to be to use this information to decide whether it's likely that you'd get a sample with a mean of 10.6 years from a population where the mean was really equal to 5. And so I'm going to redraw our t-distribution from a world where the null hypothesis is true. So again, same picture as I had on the top here, I've just redrawn it. And the idea behind hypothesis testing is that we're going to decide whether the sample we actually got would be really, really likely or unlikely based on this sampling distribution. And the way you can think about it is that if your true population mean was equal to 5, all these values that are close to 5 would be pretty likely. On the other hand, the values that are far away from 5 would be unlikely. So this one out here is also unlikely. And so values that are in these far off shaded tails of the graph are values that it would be really, really unlikely to get. And in general, it's unlikely that you're going to get something that's much higher than 5 or that's much lower than 5. And so the logic behind hypothesis testing is that if your sample mean is out here in these far off tails where it's really unlikely that you'd get it given, what your null hypothesis is, then you would reject the null hypothesis. In other words, if your sample mean is so far off that it's in one of these really, really unlikely values that you're not going to get mostly, if your null hypothesis is true, we'd say our sample is too unlikely. It's really such a small chance that it came from this null hypothesis here, from a population where the null hypothesis was true. So we're going to say, based on our sample, this null hypothesis probably isn't true. And so we're going to reject our null hypothesis. On the other hand, if your sample mean falls in this unshaded area here, where these are pretty likely values to get given, a null hypothesis of the mean being equal to 5, we're going to say this sample mean is pretty likely, given the null hypothesis that we have, so we don't have enough evidence to reject that null hypothesis. So if your sample mean is likely, we would say that we fail to reject the null hypothesis. And again, we're always going to use these terms that you either reject the null hypothesis, so you say we have evidence, against our true population mean being 5, or we'll say that we fail to reject the null hypothesis. In other words, the sample that we got doesn't provide any evidence that the population mean isn't really 5. But we're not ever going to say that we accept the null hypothesis. And the reason for this is that, thinking about sampling error, we only ever get to see the sample. So based on the sample, we can't ever say definitively what the true population mean is, because it's always possible that the sample is going to be a little different from the population just by chance. So even if we had a sample mean of exactly 5 in this example, we wouldn't be able to say for sure that the true population mean was 5. We'd have a good guess that it's pretty close to 5, but it's possible that it's something else and we just happen to get a value of 5. So we're never going to say that we accept the null hypothesis. We'll never say we have proof of the null hypothesis. Well, I guess you can't really see what I scribbled out, but that's the point. But yeah, so we'll never say that we accept the null hypothesis. We'll only say that we either reject it if we think it's too unlikely to be true, or we'll fail to reject it if it's not unlikely. So it's plausible at least. And as I said before, we're going to decide whether to reject the null hypothesis or not reject the null hypothesis based on our p-value and our alpha level. And right now I want to show you what different alpha levels look like when you're actually looking at a distribution like this. And what an alpha level really refers to is how much of these tails are shaded on the graph. And again, this is sort of a bad artist's rendering of this. That's probably not to scale. But the idea is that different alpha levels mean that different amounts of area on the graph are shaded. And the higher your alpha level, the more area in the tails is shaded. So we're going to call this an alpha level of 0.05, this an alpha level of 0.01, and this an alpha level of 0.001. And the idea here would be that the shaded area in this one would be 5% of the total graph. So here we're thinking about area under the curve again. And so your total shaded area would be 5%. And specifically, you'd have half of that 5% on one side of the graph and half of that 5% on the other side of the graph. If you have an alpha level of 0.01, your total shaded area equals 1%. And if you have an alpha level of 0.001, it's going to be equal to 0.1%. And again, what we're looking for is whether or not our sample statistic falls within the shaded area. If our sample statistic falls in the shaded area, again, based on how far out it is from the mean, which is what our t-statistic tells us, if it falls in that shaded area, we reject HO. And if it doesn't, we fail to reject HO. And it doesn't matter which side it falls on. It's all about whether it's in the shaded area or in the unshaded area. So with each of these, again, what we're looking for is whether our sample statistic is in that shaded area or not, and the test statistic tells you whether it's going to be in that shaded area. And with these different alpha levels, it's harder to reject a null hypothesis if you have a smaller alpha level. So in other words, if you have a smaller alpha level, there's more of this graph that we would say is still not too, it's not that unlikely that we would get a sample mean this far away if the null hypothesis were true. With a lower alpha level, there's more area in those tails that are shaded. So we're saying we have a lower threshold for saying that this sample is just too unlikely to have come from a population where our null hypothesis is true. And again, these are our most common alpha levels. Sometimes you'll see different ones. There's also a such thing as one-tailed tests, which we're not going to talk about, but that would be the idea that you'll only reject a null hypothesis if it's, much lower than some value or much higher. But again, we're not really going to talk too much about those, just good to know that they exist. So this is the basic logic behind hypothesis testing. And as I said before, the way we decide whether or not our test statistic falls in the shaded area is using something called a p-value. And there's actually a way to do it that doesn't involve a p-value that would require you to use the z-table or the t-table or various other tables that you have. But in this class, we're not going to do it that way. And the reason is that all this stuff is done by computer now. It will calculate a p-value for you. You will never ever be in a situation where you need to run a hypothesis test without a p-value. And I care more that you understand the ideas behind it than that you can actually look up a number on a table that'll tell you which side of this you're on. So for now, we're just going to focus on the idea behind it and then using your p-value to decide whether to reject a null hypothesis. And a p-value, so maybe I'll keep this sheet here. And the p-value, as I said before, is the specific probability of getting your sample statistic or a more extreme sample statistic, assuming that the null hypothesis is true. So I'm going to draw out this sample mean one more time. Sorry, this sampling distribution one more time to talk about what the p-value looks like. So here we have our possible sample means. We have our actual sample mean here. And we know that at some point we're going to cut off what we would consider to be the most unlikely values that you could get. What the p-value tells you is the probability of getting a sample statistic as extreme as your sample or more extreme. In other words, the p-value corresponds to the amount of the graph that's shaded at the value of your sample statistic or at a more extreme value. And because of this, the p-value will tell you whether you are at or below your threshold for rejecting the null hypothesis. Or over or below it. And the thing about p-values is that there is no easy way to calculate them based on a particular sample statistic. As I said before, this is mostly done by computer. So in this class, it'll be done by me. So I'll just tell you what the p-value is that goes with your t-statistic. But I'll just write this here, that it's calculated from the t-statistic, or if you're doing a different kind of hypothesis test, it would be calculated from whatever your test statistic is. And so basically we're saying whatever your test statistic is, it tells you how far away from the mean you are on the graph, and then this is going to correspond to some amount of shaded area here. Whatever that shaded area is will be your p-value. And so you could go through the trouble of, again, calculating what the shaded area is based on your test statistic, but I'm going to give it to you instead. But I do want you to know what the p-value is and what it corresponds to on a graph like this. As I also said in the slides, when it comes to deciding whether to reject the null hypothesis, there's basically a very simple rule that you can adhere to, which is that if your p-value is less than alpha, you reject the null hypothesis, and if your p-value is greater than or equal to alpha, you fail to reject the null hypothesis. So again, your p-value is, how likely it is that you'll get some test statistic that's as extreme or more extreme than the one you actually got. If a p-value is very, very, very small, sometimes it will be written like this. Or even, and what these tell you is that your p-value is so small, it's smaller than one of these numbers, and usually whatever statistical program you're using to spit out p-values hasn't even bothered to calculate it down to as many zeros as it has. Or it has calculated it, but it's not going to tell you. So you may see here in this class p-values that look like this, and those would just be p-values that are smaller than these numbers. Otherwise, it'll look like, p is equal to 0.02 or p is equal to 0.36, whatever it happens to be. So these are examples of what p-values could look like. All right, so coming back to our example here. Based on a t-statistic of 9.66, which is what we calculated our t-statistic to be. So if this here is a t-distribution, this is 9.66. We would say that based on a t-statistic of 9.66, our p-value is very, very, very small. And specifically, it turns out to be less than 0.0001. In other words, the probability that you would get a sample mean of 10.6 or greater, so again, you're looking at the probability of getting a sample mean of 10.6 years or greater is less than 0.01% if the null hypothesis in the population is really equal to 5. So again, if the true population mean is really equal to 5. Say that one more time. The p-value tells you that if the true population mean is 5, which is what we've written here, the chances that you would get a sample mean of 10.6 years or greater, because we're shading in all this area past that value, is less than 0.01%. So it's really, really unlikely that you would see a sample mean this big or bigger if the true population mean was equal to 5. And I'm going to write this out as well. So this means that if the true mean sentence for robbery was 5 years, there is less than a 0.01% chance we would have gotten a sample mean of 10.6 years or greater. So that's very, very unlikely. And so we've gotten to the point now where we're going to decide whether or not to reject the null hypothesis. And in order to do this, we need to set an alpha value. Let's say that our alpha value is equal to 0.05. This happens to be the most common alpha value that you see in social science, and especially in criminology and criminal justice. So we're going to go with it for this example. So now the question is, based on our alpha value of 0.05, do we reject the null hypothesis that the true mean sentence for robbery is 5 years? And the answer is yes. So we can look at it this way. You can say 0.0001 is much less than 0.05, and we know that our p-value is actually less than this number here. But since this is your p-value is less than your alpha value, this means that you reject the null hypothesis. And this, in more simple terms, means that it's really unlikely that we would have gotten a sample mean as big as we did if the true population mean was really 5.0. And so we can conclude that the judge was wrong and the true mean sentence for robbery is not 5 years. At least at a pretty good level of statistical confidence here. Finally, one other thing. When you reject the null hypothesis, another way that you can say it is that your finding was statistically significant. So in other words, you'd say that the difference between your sample and the population value you're looking at was statistically significant. And so this is what statistical significance actually means. And by the way, if you ever see something that's referred to as statistically significant in any paper you read for any class, this is what it refers to. And what it's telling you is that based on a formal hypothesis test like that, some sample statistic is really, really unlikely to occur given whatever the null hypothesis is about the population. All right, so as I said I was going to do, I'm also going to go through an example where I'm going to do less explaining along the way and just focus on the steps that you need to take in order to actually conduct a hypothesis test like this. So in this example, we're going to look at a different variable. And here we're going to say that you have a prison warden who's claiming that inmates get an average of 15 hours of visitation per month. So what we have here is a statement about something that might be true in the population. We're going to say that you take a sample of 40 inmates, and you find that there is a sample mean of 12.2 hours and a sample standard deviation of 4.9 hours. So what we're looking at here is a statement about something that might be true in the population, as well as sample data that we can use to decide how likely it is that this statement is true. So start with step 1, which is to write hypotheses. And again, with hypotheses, we're talking about a null hypothesis and an alternative hypothesis. Your null hypothesis is some statement that we're going to see if we can disprove with our sample, or fail to disprove. And we're going to write our null hypothesis using this null hypothesis notation here. So our null hypothesis is that the average number of hours of visitation that inmates get is 15. Our alternative hypothesis is whatever the opposite of that is. So if we disprove it, we'll have evidence in favor of our alternative hypothesis. And so the opposite of the number of hours being 15 is that the number of hours is not 15. And for these one sample t-tests, this is generally going to be the format for your hypothesis, where your null hypothesis is that your population mean is equal to some value. Your alternative hypothesis is that your population mean is not equal to whatever that value is. All right, so that was step 1. Step 2. Find a test statistic. And here we're doing a one sample t-test. Which means that we're looking for a test statistic called T. T, if you recall, is given by this equation. And this is the one that looks just like the equation for a z-score, except that we're talking about a t-value instead. And again, x bar is going to be our sample mean. S is going to be our standard deviation from the sample. And n is going to be our sample size. So if we look at this information I gave you up here, sample of 40 inmates means that we have a sample size of 40. Sample mean of 12.2 hours, that's our x bar, or our sample mean. And our sample standard deviation of 4.9 hours is going to be S. So we can take all this stuff and start plugging it in. Oh, sorry. First we're going to be calculating this, S sub x here. But let me add one more thing here. So we also need to do something with this value, right? So this is our value that we're subtracting here. This is your sampling distribution mean. And the sampling distribution mean, as I said before, is always going to be equal to the population mean. In the same way that the mean for a normal distribution that's a sampling distribution is going to be equal to the population mean. So to find this, you're just going to look at whatever your population mean is up here in a world where the null hypothesis is true. So in this case, your sampling distribution mean is going to be equal to your population mean, which is equal to 15. But before we can actually start plugging things in, we first have to find this term S sub x bar here. And to do that, we're going to be looking at these two. statistics. So I should have written this out first and then these two, but you can just deal with that. Okay, so we're going to use these two to find S sub x bar. And specifically, we're going to use this equation here, which is the standard deviation divided by the sample size. So to get S sub x bar, which we're going to plug in, we're going to plug in our standard deviation, which is given as 4.9 hours. And we're going to divide by our total sample size, which is 40 inmates. And if you do this math out, it should come out to 0.77. So our S sub x bar here that we're going to be plugging in to get our t-statistic is equal to 0.77. And so one thing to look out for when you do these problems, make sure you do this calculation first. Don't just plug in the sample standard deviation here, because then you get the wrong answer. So you have to have this S sub x bar in the bottom. So now we have all the things that we need to find our test statistic. We have our sample mean. This we just know from above is equal to 12.2. So we're going to plug in 12.2 for x bar. We know that our sampling distribution mean is 15. So we're going to plug in 15 for our sampling distribution mean. And we calculated our sampling distribution standard error to be 0.77. So we're going to plug this in here. Now it's just a matter of subtracting the top, dividing the bottom, and you'll get your test statistic. So the test statistic that we have here is 3.64. As I said before, every test statistic has a p-value attached to it, but I'm not requiring you to calculate those p-values in this class. Instead, I will give you the p-value. And here, a test statistic of t is equal to negative 3.64 gives you a p-value of 0.00008. Our last step is going to be to decide whether to reject the null hypothesis. And we're going to say today that we're working with an alpha level of 0.01. So the alpha level is something that will also be given in any problem, along with this other information. So step 3, decide whether to reject the null hypothesis. And specifically, we'll reject the null hypothesis if our p-value is smaller than our alpha value. In this case, our p-value is 0.0008, and it is much smaller than our alpha value, which is 0.01. So because p is smaller than alpha, we will reject the null hypothesis. In other words, we have evidence that based on our sample, the warden is not correct and is in fact overestimating the number of hours of visitation that inmates are getting. And so again, here we'd be saying that based on our sample, where the sample mean was 12.2 hours, it's really unlikely that the true population mean, so the true number of hours of visitation that inmates at this prison get, is 15 hours. And we would also say that the difference between the sample mean and this 15-hour population mean is statistically significant. So one last thing, you'd be done here, but I'm just going to draw this out to show you what this would look like on the graph itself. So here is our sampling distribution in a world where the true number of hours is actually 15 hours. And what we found is that our sample mean of 12.2 is in this really unlikely zone of sample means where chances are if you have a population mean of 15, you wouldn't get a sample this small. So this is evidence that the population mean is not really 15. And one more way to put this, in talking about our p-value and in describing these results, what we can say here is that we would only see a sample mean as small as 12.2 hours or smaller. .08% of the time if the true population mean was 15. All right, so this concludes the lecture about one mean t-tests for today. And have a great week.